Okay, welcome back to the lectures of this course. So these are the usual announcements. Just one remark about questions about the lab. It's better that you ask Sarbojit. Of course, I'd be happy to answer whatever questions you have, but I think Sarbojit is the right person to answer your questions because he's the one taking care of the lab. But as I said, I would be happy to answer questions too, if I can. So this is again the plan of the course, and we have already covered several topics. Like we started with an overview where the main message was that we would look at different kinds of properties, and we mentioned two categories: safety properties, where we say that nothing bad will happen during the execution of the program, this can be reduced to checking the reachability of a set of bad states, namely the set of states of the system that violate the safety property. And we say that in particular in this course, we would look at one property, namely linearizability, which will be the main safety property that we will look at. And in some sense, linearizability means that the computations of your program are correct, that they respect a given abstract data type. And we started to define linearizability in the previous two lectures by reasoning about what we called concurrent histories, and then identifying what we call linearization points. And the goal was that taking a concurrent history, which is generated by a concurrent program, and by identifying the linearization points of the method calls, we could reduce or transform the concurrent history to a sequential history. And in turn, we could also transform by methods that we studied previously, even earlier in the course, we could transform the such sequential history into what we call a trace, which then can be related to the given abstract data type. So in that sense, we had a hierarchy of, or a sequence of transformations that would relate the behavior of a concurrent program to that which is specified by an abstract data type. And in such a way, we could define our safety property to be that the program is linearizable with respect to the given abstract data type. Well, linearizable means that for each history that can be generated by the program, for all the histories of the program, if I take such a history, I can define the linearization points such that I get a sequential history now that satisfies the abstract data type. So this was the idea behind linearizability. And then we say that we would also, look at liveness properties. And this is something that we will do today for coarse-grained synchronization, or the coarse-grained synchronization paradigm, where we reason about threads being able to do what they want to do. So this will be something good will eventually happen. And typically in concurrent data structures, what you'd like to show is properties like wait freedom, lock freedom, and these properties, they specify progress properties for the individual threads. So not only that your program is linearizable, but each method call will eventually return. This is a typical example of a liveness property. So together, these two classes of properties, they define the total correctness of all programs. And then to specify safety properties, we studied abstract data types, and we looked at several examples of different abstract data types. For instance, the set abstract data type, where we had states, each of which is a list or a set of integers. And then you have an initial state where the set is initially empty, and then a set of methods add, where you add a new element to the set if not there, remove, where you remove an element from the set if there, and contain, which returns true or false depending on whether the element is there or not And the operational semantics of the set abstract data type was formulated using a set of rules. And then we defined a trace to be a set of atomic operations that you can generate starting from the initial state and applying the rules successively. And we say that a trace then is a sequence of atomic operations, in the sense that if you look at a trace, each element of the trace is what we call an atomic operation, consisting of a method name, an input value, and an output value. Okay, then we continue with sequential programs, and we say that the view we have of a sequential program is initially that we have a black box, and in contrast to abstract data types that generate traces that are sequences of atomic operations, a sequential program in general generates a history. And the history is a sequence of non-atomic operations. And the intuition is that an operation is not atomic because in practice it takes time, so operation takes time. And therefore we refined the notion of an operation to being two events: an invocation in which you give the method name that you are trying to execute together with the input value, and a response which comes later from the program and gives you some value. So this was the main difference between the behaviors of programs and abstract data types. And we say that using this view of a program, we could view the program as a black box with some input and output, where the input is typically a method name with an input value, and the output is an output value. And then when you perform an operation, for instance, remove two, you feed this input to the program method name and input value, and eventually you get an output value. So if you look at what happens at different time points, is that either you have an invocation in which you give a method name and an input value, or a response in which case you get an output value. And we call such a sequence of invocations and matching responses a history H. And in particular, if you have a sequential program, then the history is sequential, meaning that each invocation is followed immediately by the response. So history then, in general, is a sequence of invocations and returns, and it is sequential if the methods do not overlap. And this is the case always with a sequential program, while a concurrent program may give you histories that are not sequential. And each invocation in a sequential history is followed immediately by its response, as we see here as an example. And we say that given a sequential history, we know how to transform it to a trace by just taking each invocation and collapsing it with the matching response. And in such a way, we get an atomic operation. And because the history is a sequence of such invocations of responses, the translation of a history, which you call the trace of H, is a trace. So now you can look at the trace that you have obtained, and you can judge whether it belongs to the behavior of a set of allowed behaviors of an abstract data type, because we know what this means. So this means that because we know how we translate a history to a trace, and we know whether a trace respects an abstract data type or not, then these two things tell me that I can check whether, decide whether a history respects an abstract data type or not. So I take this trace tau, which is the trace of the history H, and because tau here belongs to the set of trace of set, then I can say that H belongs to the set of histories of the abstract data type set. Okay. So the story here is that from programs, we go to histories, and from histories, we go to traces. So from programs, we go to traces. And then we saw typical implementation of a program that implements a set. So we say that in general, when you implement such an abstract data type, you have a data structure which stores the state of the abstract data type. For instance, in the case of a set, we store the state of the set as a list of or sorted list of integers. And then you have different modules, each of which encodes the invocation or the execution of one method. So for instance, in the case of a set, we have 3 modules corresponding to the 3 methods that we have add, remove, and contain. And each one of these modules has some input parameter. So it has the method name and the input parameter as a parameter. And then outside the program, we have these 2 input ports, the inputs and the input and the output. And inside the black box, we have this implementation, which looks like here. So now if you invoke some operation with the method name, then you know which method to activate. And because you get also the input value, you can instantiate the parameter of the method. Now, given that, you go to the data structure, and the code here will do several things. It checks the state of the data structure. It possibly updates the state of the data structure, and it obtains an answer which it will forward back to the caller. So, for instance, in the case of this particular implementation of a set, so we had this sorted list of integers with sentinel nodes, H and T. And now this will be the data structure that will store the state of your abstract data type. So in this case, this corresponds to a state where you have 3 elements in the set A, 1, 3, and 5. And now you can perform these operations. So you see that I have a module for each method. So for add, we have this module here. And we say that, for instance, if you try to add 4, then what you do always, in fact, in many cases of algorithms in this course, is that you first try to locate the position in which to insert the value, if possible. I mean, if it's possible to insert the value, and you do that by locate the first key, which is not strictly smaller than the input key, the 4 here. So the locate procedure here executes this while loop, which looks inside the list, and it finds the first position, which is not strictly smaller than the 4 here, which will be the position here. And once it has done this, it looks at the current element or current key in the current node. And if it's equal to 4, this means that 4 is already there. Otherwise, it means that 4 is not there, and therefore it inserts the new node with the key 4, or a new node with the key 4, executing these instructions here. So in this case, these 2 pointers in this example, the current node, the previous node, and now you have found them using the while loop. And now you can go to this if statement and check whether you are equal or not. If not, then the element is not already there. So this means that you add the new node here with a 4. And in such a case, you have changed the state. And you have also, so you see what you did. You took some input. You looked at the state of the data structure. You concluded that the 4 was not there. You changed the state of the data structure by adding a new node in this case. And now you also give an output, which is the value that you return to the caller. So this is a typical like course of action that we will follow during this course. So even when you have concurrent programs, you have a common data structure. And although the methods the method calls may overlap, you always do this thing. You look at the state of their data structure, you inspect it, and then you change it, and then based on what you found out there, you would output some answer. So following this, this is what you get. So as we saw, so always give something, check the state of the data structure, check it, and potentially change it, and then answer some or give an answer. And in such a way, you obtain a sequential history, which you can transform to a trace, and this will be one trace of the program. Okay, so now having defined these things, we can reason about safety properties and liveness properties. And in this simple case, we just check that as a safety property that the set of traces of the program, all of them are included in the set of traces of a set. So we know what this means, traces of P. We know what traces of set means, and then we just check inclusion. And this will be my safety property. For liveness properties, we will check termination of the method call. So here we would like to make sure that each operation that is performed, each call will eventually return. And in this case, it was easy because the length of the set was finite. And because the worst thing that you can do is that you traverse the whole list, but always you terminate the while loop, because in the worst case, you will reach the sentinel, the rightmost sentinel node, and you return an answer which is either true or false, because either the if statement holds here or the else statement will be executed and you return a value. So each call will return. So, and then we started with concurrent programs, and we did this in 2 steps. So first we defined concurrent histories, and we said that in contrast to a sequential history, concurrent history is an history in which the method calls may overlap. So we still have calls or invocations and returns, matching returns, but now it's not the case that each call is immediately followed by the response. In fact, these calls and returns may overlap. So this was the notion of a concurrent history, and this reflects the fact that in a concurrent program, you may have several threads that may be active, and then the order in which the methods, the invocations and the responses occur can be arbitrary. So you get an interleaving of the threads. The only thing you know is that for a given thread, the thread is sequential, and this means that for a given thread, it's always the case that when you call, then you wait for the return before you make a next call. So we have a concurrent system of sequential processes. Okay, and this allowed us to define the notion of linearizability. And we say that in linearizability, what you do is that you take your concurrent history and you study 2 properties, an ordering on the method calls, in which one method call is ordered or precedes before, or precedes or ordered before a second call, if the first one ends before the second one starts. So this call precedes this call. So call 1 ends before call 2 starts. The interval of call 1 precedes the interval of call 2. So you can say call 1 happens before call 2. And this applies even for these 2 here. This one precedes this one. So the second criterion by which you would judge the ordering of method calls is the overlapping. And overlapping is the opposite, means that these 2 method calls, for instance, they overlap. It's not the case that one of them is completely before the other. So either one of them is included in the other, or it is the case that this one starts, the second one starts, this one ends, and then the second one ends. So you can have 2 types of overlapping. I mean, either one of them is included in the other, like this, or they have different start points and they end in the same order. But both of them are called overlapping calls. And the intuition again is that overlapping calls, they are not ordered, while ordered calls are ordered. So this is the, if you wish, the informal explanation of how we interpret concurrent histories. So these 2 method calls, they overlap also. Now we defined the notion of linearizability by defining linearization points, exactly to capture what I told you, I've just told you, sorry, namely precedence and overlapping. And we do that by identifying linearization points inside each, a linearization point inside each call. So we say that we pick our linearization points arbitrarily only that provided that they satisfy the condition that the linearization point of a method call is between the invocation point and the response point. So for instance, we can define the linearization point of this green call here to be somewhere here. And we can do the same thing for the other method calls in this history. So we are given a concurrent history H, and we are given a linearization of this concurrent history. And this allows us to obtain a sequential history. So first, one property of such a linearization is that if two methods are related by the precedence relation or by the overlapping relation, then you can choose your the linearization points to be in any order. So in this case, these two methods overlap. So I can choose their linearization points as I wish, one of them preceding the other. But if you take these two method calls, then you see that the linearization point of this one will always occur before the linearization point of this one. So linearization operation define the linearization points in the concurrent history and consider the order of the linearization points. So in this case, I have this particular order 1, 2, 3, 4, 5, 6. And then we order the calls accordingly. So this means that I take the order of the concurrent calls according to the orders of the linearization points. And this allows me to generate a sequential history from the concurrent history. H prime is a sequential history. And we say that H prime belongs to the set of linearizations of the concurrent history H. So in other words, a concurrent history has a finite set of linearizations, each of which is a sequential history, and each of which I obtain by a particular placement or relative placement of the linearization points inside the method calls. Okay. So here, by interchanging the linearization points of these two method calls, I will interchange the sequential history I generate, and I obtain a new sequential history, which I call X double prime, which again is a linearization of the concurrent history. So you see that a given concurrent history will have different linearizations. Okay, so now defining the linearization points, like I described, will give you this nice property, which is exactly what I said in the beginning, namely, if you have two calls, call 1 and call 2, and call 1 precedes call 2 in H in the concurrent history, then this implies that the same thing happens in the sequential history that you obtain by linearizing H. So in other words, precedence ordering is preserved through the application of the linearization operation to a concurrent history. So in particular, if you have, so in fact, in this case, as I told you, this happens, for instance, between this one and this one. While if they overlap again, then this property does not hold as we saw, because we can swap their order. Okay, so now we started from a concurrent history, we generated a sequential history, and now, as we know, we can generate a trace from the sequential history like this, using the collapsing operation. So linearization from concurrent histories to sequential histories, collapsing from sequential histories to traces, and in such a way, I obtain the trace, a trace corresponding to this concurrent history. So now, again, reasoning about the trace now. So this means that I can reason about traces. So I've translated the concurrent history to sequential histories and then to traces. And now I can reason about the traces, which is much simpler because I can just see whether it belongs to the abstract data type. So in this particular case, this trace that I generated, it does belong to the set of behaviors allowed by the set abstract data type. And therefore, we know that this means that H prime is a history of set, the sequential history H prime. And because H prime is a linearization of H, and because H prime is in the set of histories of set, we say that now H is linearizable with respect to the abstract data type set. So again, if you give me a concurrent history, then if I can find a linearization of the history that belongs to the set of histories of the abstract data type, then I say that H, the concurrent history, is linearizable with respect to the abstract data type. So linearization then, or linearizability, is extensionally defined in the sense that you need to find only one sequential history which satisfies the abstract data type. And then we used this linearization or the linearization operation now to reason more systematically about concurrent histories. For instance, given this concurrent history, I have this linearization and I have this place which tells me that it satisfies the abstract data type set. And then we say that, for instance, this is also a valid history with respect to sets, because you can define the linearization points as ordered here, and this gives you this sequential history, which is again in the set of histories of set. This is a valid history with respect to Qs, because you can have these linearization points which give you this sequential history, which in turn satisfies the abstract data type Q. This was not valid, because however you choose your linearization points, you will always violate the behavior of the abstract data type Q. And this means that this concurrent history is not linearizable with respect to the abstract data type Q. Why? Because I cannot find any linearization, even one, whose sequential history satisfies the abstract data type Q. So if you don't have any questions up to now, I'll just continue. So all this we have done in the previous lectures. So now the view of a program that we have is that we have different threads, each of which has its own copies of the methods or the modules implementing the methods, but the data structure is common. And in particular, because now we need to reason about linearizability of the program, we would like to show that regardless of which concurrent history the program generates, you can linearize that concurrent history in order to obtain a behavior that's allowed by the abstract data type. So in this case, we are studying sets. We have these modules, we have this common data structure. So this means that we will not only give the method or the method implementation is not only the code, but also the linearization point of the where you linearize when for a particular execution of the module or the method. Okay, so we looked at one example of a program, namely one which implements coarse-grained synchronization. So we say that the view is that you have threads that are sharing the abstract data type, and the idea is that you have a global lock which can be taken only by one thread at a time. So first, the lock is not taken if it's black, but it can be taken by some thread, for instance, the red thread, which means that now only the red thread has access to the data structure. And it can be the green thread, but at most one thread has the lock at one point of time. And this allows us to have to extend, albeit naively, the simple program that we had for implementing a set in the sequential world. And now we can extend it to the concurrent world by using a global lock. So the idea here is that if you look at the code, you see that you have first the sequential code, which is exactly the code that we used in the sequential program that implemented the abstract data type set. But on the top of that, we have, in order to enter the sequential segment of the code, you have to acquire the lock first, and then after you finish, you have to unlock. You give back the lock, you release the lock. So this means that then it's almost essentially sequential. It's just that you have concurrent threads. So you can use this program in the concurrent world, but the operation of the threads, these operations will happen one after the other. And the linearization point is that the point at which you acquire the lock. So this means that, for instance, if I have a thread at 4, it will lock first the lock, it acquires the lock, so now it's red. And now this thread can work on the abstract data type. So you have its linearization point is the point at which you acquire the lock. So we have initiated the thread with this operation at 4. And then you have the linearization point where you acquire the lock. So this is the linearization point. And then you generate these, again, now you do the locate. So you generate the pointers and you execute the while loop. You find the place in which to insert the key, which is the 4 here. And the key is not inside the set. So you will go to the else, and then you insert it inside the list. And then you unlock, and then you return true because you did not find the element inside the list, so you had to add it, and the result is true. Then you unlock the L, which means that the lock now will be given back to the system, and then you exit, which means that you have something like this. Now you may have several threads that are executing concurrently. So in this case, a red one and a blue one. So you have at 4 again, and maybe now you have at 2 at the same time starting. So these calls are overlapping now, and now there is some contention on the lock. So in this case, the red one will acquire the lock, which means that it linearizes first, while the add2 now has to wait because the lock is now taken. And now what the red thread does is that it goes to its code, it executes the code sequentially because there is no interference from the blue. The blue is blocked, and it inserts the cell in the appropriate place, after which it unlocks the lock, it releases the lock, and it terminates. And now the blue thread may start working. It can acquire the lock, and this is what happens. It has acquired the lock, it has linearized, and then it finds the appropriate place to insert the 2, after which it releases the lock and it terminates. So this is a simple concurrent history that we got by executing for only 2 threads this simple concurrent implementation of a set. So now if you look at this history, you see that our methods are overlapping. Sorry. So you see that the calls are overlapping, but the red one linearizes before the blue one, and this gives you this trace here. So what's interesting here is that the code decides for you at the linearization point, or not the code, I mean your linearization policy, which means that the policy that you use to define your linearization points, it decides the linearization points for you. And this is what I meant, that when you implement a concurrent program, you have to give me the code and also tell me where the linearization points are. But the linearization points as such, the definition is not part of the code. In this case, it can also be the case that the blue one will get access to the lock before the red one. So you have contention because you have concurrent threads, but the blue one in this case has taken the lock before. So this means that the red one will linearize after the blue one in this case. And this is another example where the calls overlap, but one of them is included in the other, and the linearization point can be in any order. So even in this case, the blue linearizes before the red. Okay, so now for all of the other methods, it's the same thing for remove and contain. So you have the locate part, but the code is protected by the lock and unlock operations. So all the time when a thread is executing, it will acquire the lock first, and then it will execute the sequential code. And in the examples that I'll show later, I will not go through the code because this code, hopefully we know now very well. We locate the position and then we perform the appropriate operation. So given this, we can now run several threads together. So for instance, if you have 4 threads again, these are the copies of the time axis for the 4 threads. So the lock is first, it's free. So it's not busy, it has not been taken by any thread. So now first, maybe the green thread will become active and tries to add 2 to the list. But before it acquires the lock, maybe even the red thread now becomes active and tries to add a 7 to the list. And maybe now the yellow thread will become active and tries to check whether 4 is inside the list or not. So see here, observe that all these threads now have initiated their codes, so they are active, but none of them has taken the lock yet. So there's contention on the lock among these 3 threads. And it's the lock, really, the locking policy that decides who takes the lock first. So in this case, it happens to be the yellow thread. So it will acquire the lock, which means that it linearizes, because we say that the linearization point is at the point, or linearization policy tells us that the linearization point for a method call is the point where the thread acquires the lock. So this means that now contain 4 has access to the list. So it goes inside the list and looks for a 4. It doesn't find it. So it releases the lock and it tells the caller, sorry, I could not find the 4 inside. So I'm done. I have released the lock. So now maybe the red thread will acquire the lock because now the lock is free. And here we have the linearization point, and this is the red thread having the lock. But before it succeeds in adding, no, in fact, it adds a 7 to the list, and it releases the lock, but it has not terminated yet. So now the lock is free. Red has not terminated, but it has released the lock. So now a 2 will become active. The green thread will become active and it acquires the lock like this. And it adds the 2 to the list. And it releases the lock. And now, in fact, it terminates before the red thread has terminated. So maybe because red is slower than green. So you see that this is a scenario where contain became active last among these 3, but it acquired the lock first. And then green became, no, red acquired the lock, but green acquired the lock after the red, but it terminated before the red. So now maybe, even now the red has not terminated, but there is a 4th thread, the blue one, becoming active. And now it acquires the lock because the lock is free. So here you see that the lock is free, so it can acquire the lock. And it goes inside the list and tries to remove a 2. And it will succeed in doing that. And it will return true and releases the lock. So now the red thread may terminate. The lock is still free. And then maybe there is another thread which tries to remove a 7. And then a yellow thread which tries to add a 7. And now the yellow one will acquire the lock first, and it looks inside the list, tries to add a 7, but it fails because 7 is already inside the list. So it releases the lock and it says that it's false. And now the red one can acquire the lock again, and it will succeed in removing the 7 and it will terminate. So in such a way, we have obtained the concurrent history, which corresponds to one particular execution of this simple program. So any questions up to now, please? Okay, so this is the concurrent history that we generated from the program. And you see that this concurrent history is valid with respect to the abstract data type set, because in fact, if you order the calls according to the linearization points, you see that I obtain a sequential history which is valid. So, and in fact, it's not difficult to reason about linearizability given this code and the linearization policy. And the reason is that the behavior of this program is essentially sequential, in the sense that it's true that the method calls may overlap, but at any given point of time, at most one thread has access to the data structure. So this means that the different threads may execute peacefully without interference from the other threads. And this makes it relatively straightforward. Although if you want to do it formally, you have to do it formally. This is not what we are doing here, but it makes it reasonably straightforward to show that indeed any history that you generate from this program is a history that can be linearized to a sequential history that respects the abstract data type set. Okay, so we say that the program then is linearizable with respect to set, because any history given my linearization policy is linearizable or reduces to a sequential history whose traces in the set of allowed traces of the abstract data type set. Okay, so now I think I'll take some questions. If not, we can take a break here. After the break, we will go through some properties of this algorithm. For instance, where you can define the linearization points, at what kind of liveness guarantees you can give. And then after that, we start with a more refined algorithm in which we do not lock the entire data structure, but we lock the cells individually. Okay, so if you have questions, you can write it in the chat and then I can answer them after the break. So now we take a break here and then we continue 1/4 past.